Before we start talking about data and data reduction, which is the first topic on the syllabus, let me just make an overall observation about the topics that we will cover prior to the first exam. You should not look for connection between those issues. This is rather similar to going off to Sears and buying a garage door opener, or as you folks say, a garage door opener. You're much fancier than I am. I buy a garage door opener, and then I rush off home with that garage door opener, and I dump everything out onto the garage floor. And I start separating pieces out, and Sears conveniently gives you a little sheet of paper so you know what you should have, what little pieces you should have, what they look like, and how many of them you should have. And that's a sort of process that we're going to go through for the first part of this semester. When you're sitting on your garage floor with the garage door opener in little pieces, you're not worried at that point, or you shouldn't be, which are the most important pieces, nor which pieces fit with which other pieces. And you should not have those concerns for the first part of the semester. What we're doing is simply an inventory check. We're going to run down all the pieces, and subsequently you will discover that some of those pieces were more important than other pieces. But at this point in time, all you need concern yourself with is coming to grips with each of the topics as we go through them, and not worry about how one topic fits with another topic. Let's then look first at data and data reduction. First of all, let's talk about levels of measurement. Data can be defined at 3 levels, or at least according to Healy, at 3 levels. First of all, let's talk about nominal level data. Data are defined at a nominal level if you simply give variables a name, if you simply label them. For example, automobiles are defined at a nominal level. There are Fords, there are Toyotas, there are Hondas, there are Dodges, and so forth. Gender is defined nominally. There are females and there are males. That is, there is femaleness and maleness. Color is defined nominally. Red, blue, green. Those are all the colors I know. Females in here will know colors like sagebrush and eggshell, pomegranate. I just know like your basic 3. However many colors you know, those colors are defined nominally. You simply give them a label because they're different and to be able to distinguish one from another. So the first observation is that when data are defined nominally, they're simply labeled. The second observation about nominal level data or nominal level measurement is that those labels are value free. Those labels imply nothing about value. Blue is not inherently better or worse than, greater or less than red. Likewise, there is no value implication when you use labels such as female or male, Protestant, Catholic, Ford, GM, Dodge, Toyota. So nominal level data are data, first of all, that is simply labeled. And secondly, those labels are value free. They imply nothing about value at all. As such, nominal level data are the least useful, at least statistically, the least useful kind of data that can exist. You can do less with nominal level data than you can with any other kind. Let me talk about each of these levels of measurement, and then we'll have an opportunity for you to ask what questions you have. A second and higher level of measurement then is ordinal level measurement and ordinal level data. Ordinal level measurement and ordinal level data. Data that are defined ordinally are rank ordered. Data that are defined ordinally are rank ordered. When Ford makes the claim, for example, that they are the number one seller of trucks, they are defining themselves or their sales ordinally. If we were to have three sellers of trucks, Ford, GM, and Dodge, we could rank those manufacturers ordinally. We could, for example, note that the biggest sellers of trucks were Ford, followed by GM, and followed by Dodge. Clearly, this sort of data, unlike nominal level data, is value laden. That is, there is the implication of highest or lowest, best or worst. We can make statements from this sort of arrangement that Ford sells more trucks than either GM or Dodge. We can make statements of the sort Dodge sells fewer trucks than either Ford or GM. But that is the limit. That is the extent of the sort of statement that you can make from ordinal level data, data that is rank ordered. And it is the limitation of ordinal data because each of the differences, that is the difference between Ford and GM and the difference between GM and Dodge, is equal. Because the difference between 1 and 2 is equal to the distance between 2 and the difference between 2 and 3. Yes. If we were to actually have some record of how many trucks Ford and GM and Dodge sell, and were to discover that Ford hypothetically sells 100,000 trucks, GM sells 50,000 trucks, and Dodge 40,000 trucks, we would note that, minimally, we would note that the difference between truck sales between Ford and GM was a substantial one, whereas the difference between sales by GM and Dodge was relatively small. That sort of scaling, would you agree, is absent when you rely upon the rank orderings of 1, 2, and 3. Because when you rely on rank ordering, the difference in truck sales between Ford and GM, 1 and 2, is equal to the difference in truck sales between GM and Dodge, 2 and 3. So that ordinal level data are, first of all, data that are defined in a rank-ordered or measured in a rank-ordered way. And secondly, the limitation of ordinal level data is that the true differences between the stimuli are equalized, so that the true differences are lost and the differences become equal. Yes, because the difference between 1 and 2 is equal to the difference between 2 and 3, and equal to the difference between 3 and 4, and so on and so on and so on. Ordinal level data, because you can manipulate them in some way, are more useful than nominal level data. But as you will see, less useful than interval ratio level data. And let me talk about interval ratio level data. Healy combines interval and ratio level data, or interval and ratio level measurement. Other authors discriminate between these two levels of measurement, discriminate between interval level data and ratio level data. Let me give you an example of interval level data. And much communication research involves interval level data because we're often not interested in observable behaviors. We're often interested in the things in people's heads. How much they like something, what they think about something, how much they know about something. And absent the ability to simply open up somebody's skull and fiddle around inside and count something in an objective way, we have to use pencil and paper measures. And we typically use pencil and paper measures that are defined at an interval level. And I'm sure you're familiar with these. The sort of thing that says, indicate on the following scale how happy you are. And what you find is a scale that is anchored at one end by very unhappy, at the other end by very happy. And in between appear a series of numbers. 1, 2, 3, 4, 5, 6, 7. Yes. If you have, and this is sort of common in not only in communication research, but in sociology research, psychology research, and so on. If you have very happy, 7, 6, 5, 4, 3, 2, 1, and then very unhappy. And I'm running out of space, so they're very unhappy. With these scales, you're asked to circle the one number that best represents your feelings. If you feel happy, for example, you might circle 6, or you might circle 7. If you're unhappy, you might circle 3 or 2, or if you're extremely unhappy, you'd circle 1. Yeah. Clearly, the intervals on this scale, that is the difference between 7 and 6 and 6 and 5 and 5 and 4 and so on, are equidistant. They're equal. So that the adjacent scores, all adjacent score pairs are equidistant from one another. But you and I can say that person A, who circled a 6, is significantly more happy than person B, who circled a 2. So interval level data allow for fairly sophisticated statistical manipulation. The difference between interval data and ratio data is that interval level data lack a true 0 point. They lack a true 0 point. That is not true of ratio level data. Ratio level data are measured on scales that have a true 0 point. Let me give you an example of interval level data. Degrees Fahrenheit. If you go outside and it's toasty and warm and not like it's going to get today, I may as well be in England, You know, I've now been in Texas so long, my blood is like water. So when it gets down to chilly, I get very unhappy, very grouchy. You would admit, I think, that degrees Fahrenheit, like degrees centigrade, are measured on scales where the values are separated by equal intervals. That is, the difference between 80 degrees Fahrenheit and 79 degrees Fahrenheit is exactly the same as the difference between 57 degrees Fahrenheit and 56 degrees Fahrenheit. Yes? However, when you're measuring in degrees Fahrenheit or degrees centigrade, you cannot make this sort of statement. You cannot say that 80 degrees Fahrenheit is twice as warm as 40 degrees Fahrenheit. You cannot say that 20 degrees centigrade is twice as hot as 10 degrees centigrade. Because neither of the Fahrenheit scale nor the centigrade scale contain a true zero. They contain an arbitrary zero. For example, degrees centigrade, would you agree that the 0 point is the point at which water freezes? Absolutely arbitrary. Why not the point at which Heineken freezes? It would be much more useful to me. If I knew the point at which Heineken freezes, a lot more useful. I wouldn't get into trouble when it freezes and you can't get it out of the bottle, and by the time it's unfrozen or thawed, I guess is a better way of expressing that, by the time it's thawed through, you don't even want the thing. You probably just throw it out anyway. Because you figure it's no good. It's like pork. You can't cook it and let it heat, cool down. I don't know. The microorganisms growing. There's the same things going on in Heineken, I'm sure. But you understand that it's absolutely arbitrary to decide that your 0 point is the point at which water freezes. We could have selected the point at which Heineken freezes, the point at which alcohol freezes, the point at which something else quite arbitrary happens, the point at which human bone melts. And because this 0 point is arbitrary, you cannot make comparative statements. You cannot, as I've indicated, make this the sort of statement that 20 degrees centigrade is twice as hot as 10 degrees centigrade, or 80 degrees Fahrenheit is twice as hot as 40 degrees Fahrenheit. You go outside on a day when it's 40 degrees and you are chilled. If you're like me, you've got about 9 layers of clothing. 80 degrees Fahrenheit, when you stop and think about it, is so much warmer. It's more than twice as warm. Subjectively, it's like 40 times as warm. It's got to be at least 9 times as warm because I've only got 1 layer of clothing on. Maybe 2, 80 degrees Fahrenheit. So, this will not become an issue throughout the semester, but Healy talks in terms of interval ratio level data. You should understand simply that when he does that, he's combining 2 levels of measurement that can be distinguished, and distinguished on the basis of the presence or absence of a true 0 point. Nonetheless, interval ratio level data are, statistically at least, the most useful because you can manipulate them and make complex statements about those sorts of data. For example, and we could say this, 10 degrees Kelvin is twice as hot as 5 degrees Kelvin. Why can we say that? Because degrees Kelvin are measured on a scale that actually includes a true 0 point. 0 degrees Kelvin indicates the absence of all heat. Sometimes we deal with, in communication with ratio level data, if you're observing interactions between people and counting, for example, the number of questions that each person asks, if one person asks 6 questions and the other 3 questions, then person A, you can say, asks twice as many questions as person B. And you can make that very complex comparative statement because number of questions asked is measured on a scale in which 0 actually indicates the absence of questions. If you measure somebody who's 6 feet tall is twice as tall as somebody who's 3 feet tall. Because feet and inches, whatever, or meters, whatever scale of measurement of height you use, is a scale in which 0 is a true 0 point. It equals the absence of height. Weight is the same. 0 indicates the absence of weight, so that somebody who's 200 pounds is twice as heavy as somebody who is 100 pounds. So that as you move up through these levels of measurement, from nominal to ordinal to interval ratio, the data that is derived from such measures becomes more and more statistically useful because you can manipulate it and make more and more complex comparisons. Having said that, are there any questions about levels of measurement? Or am I so skilled at lecturing that it's crystal clear? Or are you so afraid to use the technology that you're going to keep your questions to yourself until we've stopped taping and you can come up and ask me privately? There's no private question asking in this course. Are there any questions about levels of measurement? Well, the first part of this course, as I've said, is sort of like going through the box you bring home from Sears. It's also sort of like a CD. That's the end of that track. That's the end of levels of measurement. It was just a short intro track. Some of these tracks will be longer than others. Some you will like more. You will actually say that again, Doctor. That was a good track. We want to hear that again. The next thing I want to talk about then is data reduction. Data reduction. On page 37 of the Healy text, there is a data set towards the bottom of that page. And the data set involves 90 hypothetical scores, or 90 scores taken from 90 hypothetical residents of a retirement community. And the data indicate the number of visits that those 90 residents received during the previous year. So that if we were to read this data set, the score in row 1, in column 1, row 1 is a 0, that would simply indicate that that person received 0 visits during the year. In row 1, column 2, there is a score of 52. That would mean that a second person received 52 visits during the year, and so on through the 90 individuals. Yes. When you look at that data set of 90 scores, how meaningful is it to you? How easily can you communicate to others about it? We have an awkward pause. It's not awkward because I presume that you understand that this data set isn't very useful, or this data is not very useful in this form at all. You don't expect this to be the way in which data is given to you. You don't expect economists to come to you and say, well, I've got data on all sorts of things. from the past year, and here it is, you try and make sense of it, because, I can't. Or meteorologists to come to you with data and say, well, here's all the data, you sort of make sense of it. You expect, and I expect, data to be presented in a more coherent way. That is not to say that this data set is meaningless. You clearly understand and can interpret the 90 scores. You know, for example, that at least one person received no visits per year. At least one person received 52 visits during the year, and so on and so on. The point is that this is as complete and at the same time as meaningless as data can become. What you and I and everybody else is almost automatically engaged in is data reduction. That is, somehow transforming, in this case, these 90 scores into fewer than 90 scores, often into a single score. A single score that is intended to represent all 90 scores in some way. And that is certainly a much more efficient way of expressing the information. That is, clearly we could compute the average number of visits received by these 90 individuals. That is a much more efficient way of presenting information about the data set than is to simply present the 90 scores. But you understand, when you compute an average, when you find a more efficient way of expressing information, you typically lose some amount of the original information. If we were to compute the average number, and we shall, if you compute the average number of visits received during the year, for example, by these 90 residents, you lose the richness of the information. You have no idea, for example, if given simply the average, what the highest number of visits and what the lowest number of visits were. That is, you have no idea the extent to which the group of 90 varied in regard to the number of visits they received. In general, then, data reduction involves a trade-off. And the trade-off is between increased efficiency on the one hand and ability to retain as much of the original information as possible on the other. The trade-off is between, on the one hand, the efficiency of the expression, and on the other, ability to retain as much of the original information as possible. Are there any questions about the general nature of data reduction? The most straightforward way of manipulating these 90 scores is to create a frequency distribution. And here is a frequency distribution of the 90 scores. We'll try and work this through. As I'm sure most of you are familiar with, when constructing a frequency distribution, you have two columns, lowercase x subscript I, which simply means each individual score. In this case, each individual unique score. We have 90 scores. That is, we have lowercase x1 through lowercase x90. Simply the general way of making that statement is that there are some number of xi's. There are some number of individual scores. So one column is headed x, lowercase x subscript I, and the other column is headed f, which simply indicates the frequency with which each of those individual scores appears in the data set. In this data set, the lowest score is 0. And if you scour through this data set, that is, if you scour through the 90 scores, you discover that there are 6 zeros. The next highest score is 1. And if you scour through the set, you'll find that there are 2 ones. The next highest score is a 2, and there's one of those. The next highest score is a 3, and there is one of those, all the way down to 52, and there are 4 of those. So the scores range from 0 to 52. And if you sum together these frequency scores, you should arrive at the total number of scores, which in this case is 90. Are there any questions about the nature of a frequency distribution or how to construct a frequency distribution? I want you to remember this at the end of the semester when it says, as you evaluate the course, clarity of instruction. Crystal clear, you say. Crystal clear, couldn't have been better. It was almost actually too clear at times. Are there any questions about frequency distributions at all? Before we meet or by the time we meet next time, first thing that I would like you to do then is to construct the frequency distribution that I've constructed. That is, to construct the frequency distribution for those 90 scores on page 37 of the text. The 90 scores that reflect the number of visits each of 90 residents of a retirement community received during the year. Okay. And I will put the answer, that is the accurate, what I hope to be the accurate frequency distribution. You may discover I've done wrong. I will load that onto WebCT so that you can, certainly by next Tuesday, by the time we meet again, you can check your answer. Let me ask you this. When you construct frequency distributions of the sort that I've constructed here, have you retained all of the original information? Yes, you have. None of the original information has been lost. And remember, our two considerations were, on the one hand, the efficiency of the outcome, that is, the efficiency of the way in which the information is presented, and on the other, ability to retain as much of the original information as possible. We have scored very well on the second criterion. That is, we have retained all of the original information. No scores were lost. You know exactly what scores appeared in the set, how often each score appeared, and so on. How efficient is this? How efficient is a frequency distribution? I hope you're sitting there thinking, not very. Not very. That is, we have not scored very well on the first criterion, ability to express information in an efficient way. We will spend some time looking at ways in which we can express information. And we will do that in two ways. First of all, and this is something of a cul-de-sac that we're going to take ourselves into. We're going to examine ways in which we can express parts of this data set, or express various aspects of the data set. We will then engage in a much more fundamental and a much more important discussion of how we can express, on the one hand, the center of this data set or any data set, and on the other, how we can express the variability inherent in the data set. And those are the topics following data reduction. That is, first of all, measures of central tendency, and second, measures of variability, that are covered in chapters 3 and 4 respectively, which should indicate to you that you should get toward reading those chapters. First of all, however, let's look at ways of expressing various pieces of information about the data set that we have here. And really, you can do this, of course, with any data set, any frequency distribution. Let's take a look at, first of all, at proportions. Proportions, P, equal F divided by uppercase N. That is, the frequency divided by the total number. F is simply notation for frequency, as I've indicated, and N is notation for group size, number of people involved, number of scores involved in the data set. Let us then take as an example the proportion of residents receiving less than one visit per month. The proportion of residents receiving less than one visit per month. And this is the second thing that I want you to do between now and the next time we meet. That is to compute the proportion of those 90 residents who received, on average, less than one visit per month. How are we going to do that? Let me ask you this. If a person received, on average, one visit per month, how many visits would they receive during the year? No, somebody press and remember the technology.
12.
12. Thank you. If you received 12 visits, there being 12 months in the year, you would then receive on average one visit per month. Therefore, if you're interested in those people who received on average less than one visit per month, would you agree that you're interested in those people who received 11 visits per year or less? You don't have to click and tell me anything, but you do have to become animated in some way. You do have to nod or go. No. If you receive 6 visits per year, you receive on average one visit every 2 months. If you receive 11 visits per year, you receive on average 11/12ths of a visit per month, which is less than one visit per month. So F here, when you're computing the proportion of all these residents who received on average less than one visit per month, that is the numerator, F, you're interested in the frequency with which scores between 0 and 11 occur. As it turns out, there is no 11 in the set, and there is no 4 or 5 in the set. So in order to compute the frequency of residents who received on average less than 1 visit per month, you would add together all of the frequencies associated with XIs of less than 12. The proportion then is equal to F over N. N here is 90. Would you agree? The total number of residents, the total number of scores is 90. So to compute the proportion that I've asked, you would simply add together the relevant scores to provide you with the numerator F, and then the denominator is 90, and you would then express that score in decimal form. Are there any questions about how to compute a proportion? You have to press whatever you want me to do.
Can you move the pen down some?
No, I can't move the pen down because the answer is under the pen. Okay? In fact, I should move the pen up, because I've actually computed the answer. Yeah. And I'm not giving it away until next time. It's unless you're willing to come and paint my house.
Will you show these on WebCT, like the steps?
Yeah, I will post onto WebCT the frequency distribution, and I will post onto WebCT how to compute the relevant proportion and the correct answer. You should obviously go through those computations yourself first. Don't try and work your way to the correct answer. That is, don't look at the answer and then sort of work back from there. You're going to have to do these things on an exam, and you won't be able to do that on an exam. The last place, in this case, the last place you go to is WebCT. I'm interested, and you should be interested, not in whether you get the right answer. I'm not interested if you plug in the right numbers, in a sense, keystroke in the numbers correctly. I'm interested in whether you know how to do it. If you make an error in the computation, if you keystroke in a 9 instead of a 6, I don't care. You shouldn't care. What you do need to care about is, or what you should care about is, whether you can work your way through the process. Are there any other questions about proportions? If not, let's move on to percentages. And a percentage is nothing more than F divided by N multiplied by 100. That is, it's P, the proportion, multiplied by 100. If you were to discover that the proportion of residents who receive, let me simply go through an example. You will find that if we were interested in the proportion of residents who receive 0 visits, that equals F divided by N. Well, you would discover that the frequency, the number of people who received 0 visits was 6. The total number of, that is N, the total number of scores or residents is 90, so that P equals, I think it's 0.067. If you were now interested in the percentage of residents who received no visits a year, these poor, pathetic, huddled 6, abandoned by their families, probably at least borderline suicidal, sitting in their rooms alone, eating Jell-O, perhaps sucking it through a straw. The future that is in front of all of us. If you were interested in expressing this not as a percentage, not as a proportion rather, but as a percentage, you would simply multiply P by 100. That is, you would put it on a base of 100, which is 0.067 multiplied by 100, which equals 6.7%. Yes. Yes.
So is a 0.067 the proportion then?
That's the proportion. And the percentage then, when that information is expressed as a percentage, it's 6.7%. Are there any other questions about proportions or percentages? The last thing then that I eventually got it oriented correctly, I should have noticed that everybody out there was sort of like this. The last thing, measure that I want to look at is ratio, R. Ratio, or R. And R equals F1 divided by F2, where F1 is the frequency of the first event and F2 the frequency of the second event. If we were then interested in, and the problem here I've quickly realized is, again, I'm left-handed, and this world simply abuses left-hand people. This is all oriented for somebody who is right-handed. It's absolute discrimination. I'd be a lot cleverer and a lot funnier, a lot happier if there were a left-handed oriented, or if I were right-handed. I would be a lot less intelligent, because we all know that left-handed people are much. No. If we were, for example, interested in the ratio between persons who received 0 visits per year and persons who received 1 or more visits per year. Yeah. The frequency of the first event, as we've indicated, is 6. There are 6 pathetic individuals who receive 0 visits per year. I'm going to be like this. My daughter may call me Christmas morning, and then she'll call me Christmas Eve, and then it'll turn into sometime around Christmas. We have 6 individuals we discovered in this community who receive 0 visits during the year. Would you agree that there were 90 people in all? So the number of people who received at least 1 visit per year is 90 minus 6. So the ratio is 6 divided by 84. Yes? Which I think is 1 over 14. Obviously, I want you to compute the ratio of persons who received at least, the ratio of persons who received less than 1 visit per year, per month. Let me say that again. I want you to compute the ratio between persons in the community who received, on average, less than 1 visit per month, with persons in the community, on average, who received at least 1 visit per month. Can I repeat that? Of course I can repeat that. Well, listen. Can you paint my house? I want you to compute the ratio between persons in the community who received, on average, less than 1 visit per month, with persons in the community who received, on average, at least 1 visit per month. Yeah? And again, I will put that answer and how you get to it on WebCT. There are now people who are looking at one another like they're on board a flight across the Atlantic, and they were told, and you know how you can sit there and periodically they will go through the altitude. There are folks out there who look like that altitude number is going rapidly from like 32, 31,000, 30,000, 20. We're on a downward trajectory. We're going to hit water in a minute. Okay. Are there any questions?
I thought that that's what you just did, was computed that, so I'm completely
No, I didn't.
lost.
What I did was I computed the ratio between persons who received 0 visits and persons who received at least 1 visit per year. What I want you folks to do is compute the ratio between persons who received on average less than 1 visit per month with persons who on average received at least 1 visit per month.
So it was per month, and I was getting confused because you were doing the year. That's right?
Yes. And I'm getting confused because there are people, it's like we're in a Lord of the Rings thing. There are hobbits above us. Are there any other questions?
Is this all a
No.
have to do?
Pardon?
Is this all
No, you're going to have to press and hold and not just lean forward.
Okay. Is this all the math that we're going to have to do?
No, you'll need to do calculus in your head somewhere in the 3rd week. Yes, if you can multiply 9 by 9, and if you have a calculator that will display square roots, you're home and dry. There is no mathematics involved. There is arithmetic involved. And really that's very, very different. Most of you, or no, let me not say most of you. Let me not even refer to you. Historically, I've taught the course since the year 627. I've gone through bloodletting, I've gone through looking at tea leaves, I've gone through dealing with the entrails of animals. Teaching research methods in the 14th century was a completely different thing. A lot more animals and a lot more blood and gore. It's less interesting now. Since I started teaching this course, which is about 20 years ago, obviously any number of communication majors have passed through the course. Literally thousands. Which is a problem for me because many of you work in restaurants as students. And my wife is now fearful to go into any restaurant where there's a communication major who's been through this course working, because we don't know what happens to the food before it gets to us. Didn't do well in the course. I hated that course. I hated Douglas. Yeah, he wants secret sauce. We'll give him secret sauce. Let me finish this observation and then I'll take another question. Historically, I've discovered students come into this course believing fearing mathematics because they believe themselves unskilled in that area. The reality of the situation is that is not true. The reality is that each of you, with that concern, has that concern, not because you are inherently unskilled mathematically. It's as a function of either one, poor teaching, or two, simply being told you're not very good at it. I have no doubt, based upon the thousands of students who've been through the course, that every one of you ultimately, not ultimately, very quickly, will discover that the easiest part of the course is the number stuff. You will take the first exam and you say, you know, I did fine on all the questions that involved computation. It was the other questions I didn't understand. My point is really straightforward, that don't worry about the arithmetic. Don't worry about the arithmetic. If you get questions, these trial questions, incorrect because of the arithmetic, we can fix that in no time. If you can't do these problems because conceptually you don't understand what's going on, the solution to that is much more radical. One is just some therapy, the other is invasive surgery. You know. Was there a question over here?
Yes, there was. Since we're not supposed to worry about the computation, are the formulas going to be on the test? So we're just like plugging in, or do we have to memorize it?
You will have to memorize the formulae. All the formulae in this course you will have to commit to memory. And I'm not embarrassed by that. You should not be afraid of formula either. You're not afraid of words, and there's no reason, therefore, to be afraid of a formula. A formula is simply the most efficient way of expressing an idea. If P equals F over N, that is telling you that in order to compute the proportion, you divide F by N. It's just words. It's just words. You simply have to know what F and N represent. And in this case, F equals the frequency, the number of people who do something or who receive something, and N is the total number of people. So, yeah, you do have to commit the formula to memory, but you should not be disturbed by that because it's just words expressed efficiently.
I'm sorry, but I mean, whether it's arithmetic, mathematics, anything that's dealing with numbers, I happen to think it's the root of all evil after money.
Well, I tell you, we can debate this, or we can simply say that this is a course in research methods, and unfortunately, you know, the world is becoming more empirical rather than less empirical. When you decide your diet, when you decide which medication to take, when a physician decides for you which medication to take, how much medication to take, you want empirical data to support those recommendations. You don't want this person looking at the entrails of a pig, right? You don't want this person reading a book by E. Annie Proulx that has nothing to do with medicine and has no data, but is really quite enjoyable, and you know, you can talk to neighbors about it and sound educated. No, you want the person to have dealt with numbers, yeah. And I'm willing to bet you by the end of the semester, you will be able to do that, the numerical part of the work, very, very easily. Very, very easily. I promise you. That is the easiest part of the course. Between now and next time, generate the frequency distribution, the proportion, the percentage, and the ratio, and start to read, first of all, the material dealing with measures of central tendency, but also then the material, dealing with measures of variability, because those are two related issues. One of them, hang on, don't rush. We've got plenty of time. We're cycling along here in an orderly way. One of those measures of central tendency involves discussion of specifically the mean or average, mode, and median. Most of you are familiar with that stuff. Measures of variability, the range, variance, and standard deviation, some of you will be familiar with, but some of you will be unfamiliar with. So read those two chapters, or at least the parts of the chapter that I've indicated to be relevant to our discussion. And we will, next time, first of all, go over the problems I've set today, and secondly, then, talk about measures of central tendency. Bon appetit.